Good day, class. Today we're going to start our second unit, which goes in depth into polynomial functions. So we'll talk about transformations a little bit more. We'll go into the leading coefficient test and end behavior, zeros of polynomial functions, and the intermediate value theorem today. All right, so here's our parent function, cubic function. All right, we'll just go over some of the basic details of this. All right, so our domain, of course, there's no square roots, there's no variables and denominators, so this is all real numbers, or negative infinity to infinity. Our range, we can see from the graph, this thing would continue down forever and go up forever, so the range is also all real numbers. The intercepts, it has one intercept, which is simultaneously the x and y intercept. All right, increasing, it's obviously increasing here, and it's obviously increasing here. However, if you zoom in really, really close, like if you were to graph this on your graphing calculator and zoom in, if you zoom in right here, you see that it's actually incrementally still increasing. So it's actually increasing everywhere. So from negative infinity to infinity. Well, if it's increasing everywhere, then it's obviously decreasing nowhere. Remember, that is the symbol for the null set, which is an empty set. Is this even, odd, or neither? All right. Well, it's obviously not even. Remember, we talked about even being symmetric about the y-axis. This is obviously not symmetric about the y-axis. Odd, we said, is symmetric about the origin. All right. And another way to think about symmetry about the origin is any point that you have on the graph, x, y, you have the point negative x, negative y as well. So here's a nice point. We have 1, 1. Which means we should have the point negative 1, 1 as well, and we do. If you went up even further, you plug 2 into here, you would get 8, so 2, 8. If you plug negative 2 into here, you would get negative 2, negative 8. So yes, this thing is odd, and we know that any odd functions are symmetric about the origin. Okay. So the leading coefficient tests, all right? So first we need to talk about, the standard form of a polynomial, all right? So if we have a times x to the nth plus b times x to the n minus 1 plus c times x to the n minus 2, right, plus dot, 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 plus, you would eventually have some, it doesn't really matter what letter we want to call this, let's call it j, x to the first, all right, plus some k. All right, so of course, when we put it in standard form, our x's start, our powers of x start at the highest power, and then they gradually drop down until, of course, we get, this really would be x to the 0th power, right? Because anything to the 0th power is 1, so that's really just the same thing as just k, right? So this is the n that they're talking about here, all right? So when n is odd, if this thing is an odd power, all right, and a is positive, all right, then our leading coefficient, then our end behavior, all right, this helps us with end behavior, all right, and really, I'm sure in Algebra 2, your teachers talked about as x goes to negative infinity, f of x goes to something, right, positive or negative infinity, and as x goes to positive infinity, f of x goes to something, either negative or positive infinity. To me, that's an awful lot of work, all right? A lot of writing for something very, very simple. So I don't care if you just draw arrows, right? Um, so instead of A being positive, I'm going to kind of rewrite this. So um, when n is odd and your leading coefficient is positive, all right, then your end behavior goes like this. You go down to the left and up to the right. So down to the left, or falls to the left and rises to the right. You may often hear it referred to like that also. This is basically saying, okay, as x goes to negative infinity, then f of x goes to negative infinity also. And here, as x goes to positive infinity, f of x goes to positive infinity. Right? If your leading coefficient is negative, so we'll just quote all of that stuff, right? Then you go up to the left and down to the right, all right? This is actually really easy to think of in terms of just very easy odd-powered functions, right? Like if f of x equals x, all right, well, that graph looks like this, right? So my leading coefficient is positive, my n is odd, so I fall to the left and rise to the right. That fits this pattern, right? If f of x equals negative x, of course that's still to the first power, so now my leading coefficient is negative, and my n is odd, all right, well, the line negative x, it looks like this, right, which rises to the left and falls to the right. Right? So you can think of it in terms of just kind of very basic, um, odd functions. Right? Even the one that we just talked about, x cubed, right? Well, positive x cubed, we just looked at it, we know it goes like this, right? Which obviously falls to the left and rises to the right. And negative x cubed, of course, would look like this. Right? Again, which would rise to the left and fall to the right. Right? When n is even, right? And your leading coefficient is positive, right? You are going to rise to the left and rise to the right. Right? Of course, if your leading coefficient is negative, right? And of course, this n is even is just saying that you have your highest powered x is even, so x squared, x to the fourth, so on. Going to fall to the left and fall to the right. Of course, we can always look at our most simplistic even powered functions, right? If we look at f of x equals x squared, well, this is just our parent function polynomial, right? So it's going to look like this. Well, it has a positive leading coefficient, and my n is an even number, so we go up to the left and up to the right, which this fits that pattern. Of course, if we have f of x equal to negative x squared, right, that would just be a parabola that opens down, so of course that would fit this also, right? A leading coefficient that is negative, a power, when my n is even, all right, then we would fall to the left and fall to the right, which obviously is what happens here. All right, so before we get into examples, all right, an excellent little chart to have for this, I would recommend. So all right, so over here, if we have even, and odd. And over here, if we have positive and negative, right? So this would be my leading coefficient, and up here would be the degree of the polynomial, right? Which is just the highest power of x, right? Well, if my degree is even and my leading coefficient is positive, we know that that rises to the left and rises to the right, right? If my degree is even but my leading coefficient is negative, we know that that falls to the left and falls to the right. If I have an odd degreed polynomial with a positive leading coefficient, I know that I fall to the left and rise to the right. And if I have an odd degree polynomial function with a negative leading coefficient, right, I know that I rise to the left and fall to the right, right? So this is definitely what you would want to have in your notes, or what you would want to have somewhere handy when you're doing any of these types of problems. All right, so use the leading coefficient test to describe the right hand and left hand behavior of the graph. All right, well, here I have an odd powered polynomial. I have a negative leading coefficient. So according to my chart, that rises to the left and falls to the right. That's it. Done. All right. Like I said, if you really want to be really mathematically technical and do a lot of writing for this, you would say this is the same thing as x goes to negative infinity, f of x goes to positive infinity, and as x goes to infinity, f of x goes to negative infinity. Right, so this is the same thing as all of that. I think it's much easier to just draw these arrows than to write all of this out. If your Algebra 2 teacher was a stickler for writing all of this out, and that's just kind of what's been ingrained to your mind, by all means, write that out. I will know what you mean. All right, so the leading coefficient test. If you're watching this video, I highly recommend that you pause it and kind of just do these very quickly on your own. And then when you unpause it, just check yourself. All right, so here we have an even degreed function with a positive leading coefficient. So this is going to be up, up. All right, here we have an even degreed polynomial with a negative leading coefficient. So this will be down and down. Here we have an odd degreed polynomial with a positive leading coefficient. So this will be down to the left, up to the right. And here we have a negative leading coefficient with an odd degree polynomial. So this will rise to the left and fall to the right. Right. Now do, of course, keep in mind, this is only end behavior, right? We have no idea what's going on in the middle of these graphs, okay? This is just what happens at the outsides, at the ends. All right, zeros of polynomial functions. It can be shown that for a polynomial function f of degree n, the following statements are true. All right, the function f has at most n real zeros, right? Which obviously makes sense. That's actually the fundamental theorem of algebra, right? So if you have a first degree polynomial, which is just a linear function, you're going to have one solution. If you have a second degree polynomial, a quadratic, then you can have two solutions, right? So on and so forth. So third degree 3, fourth degree 4, 10th degree 10, right? Now it says at most, because here we're only talking about real zeros, okay? Some of them can be imaginary, as you should have studied when you studied quadratics in Algebra 2, right? Also, it's important to note, and we'll get to this in a little bit also, that imaginary solutions always come in pairs, right? So if you have one imaginary solution, you must have two, right? So you can only have even numbered imaginary solutions, right? Also, the graph of f has at most n minus 1 relative extrema. All right, extrema are maximums and minimums. All right, so we kind of talked about that a little bit last unit. All right, so if you have some graph that does some stuff like this, oops, okay, we'll start over. So if we have some function that does something like this, right? This is a maximum, this is a maximum, this is a minimum, this is a minimum. Now we fall to the left and rise to the right, which means we know this has to be some odd powered function, right? And of course we have 1, 2, 3, 4 maximums and minimums, which are called extrema, right? So in all likelihood, this would be a 5th degree polynomial. Okay, do recall that a zero of a function f is a number x for which f of x equals 0. All right, so that means when you plug this number in for x, your y is equal to 0. All right, that's what a zero of a function is. Zeros have many names. All right, zeros we often call solutions. Zeros we call them roots. All right, and these are more, in fact, all three of these are kind of algebraic. All right, graphically, all right, we call them x-intercepts. All right, so solutions, roots, zeros, x-intercepts, these are all the same things. All right, so it is important to note that. All right, so find all real zeros of f of x equal to x cubed minus x squared minus 2x. All right, well, typically we like to factor. All right, and in this case we can because every term here has an x. So we can pull out an x as a greatest common factor. And when I do that, I'm left with x squared here, minus x here, and minus 2 here. All right, well now this is a nice quadratic that can also be factored. All right, and this will factor to x minus 2 and x plus 1. All right, again, guys, I can't emphasize this enough. You should have done lots of factoring, both in Algebra 1 and Algebra 2. If you can't factor, especially this is like the easiest thing that you could ever factor. If you really struggle with factoring, definitely go back on your own and brush up on factoring. Okay, I don't really have enough time in this course to go through an entire factoring lesson. You should have done lots of factoring both in Algebra 1 and Algebra 2. If you're really, really struggling with it, contact me. All right, we can get together. You can come in before school, after school. We can do a Google Meet, whatever. But you need to know how to factor to pass this course. Right? If you cannot factor, you are really, really, really going to struggle. Okay, so anyway, now that we have this thing nice and factored, it wants to find all real zeros, which means we want f of x to equal 0, right? Well, when we have multiple factors set equal to 0, you can set each factor equal to 0. Now, the important thing here is don't forget about this x. All right, this x being out here by itself is still a factor. Just because it's not in parentheses with some other number, it's still a factor, right? So I would say, okay, x equals 0, x minus 2 equals 0, and x plus 1 equals 0. I set each factor equal to 0, and then I solve. Well, this requires no work to solve. It's done. Here, I just add 2 to both sides. Here, I subtract 1 from both sides. So all of my zeros, all of my solutions, all of my roots, all of my x-intercepts are these. X equals 0, x equals 2, and x equals negative 1. Right? Again, we're doing the same thing. Right? So you might want to pause here. All right? work this out on your own, then check your solutions with my work. So again, all of these things have an x in them, so we can go ahead and factor out an x, and then I'm left with x squared minus 12x plus 36. All right, so again, this is a nice factorable quadratic that will factor to x minus 6 and x minus 6, which you also could rewrite this as x minus 6 quantity squared, right? Anything times itself is that thing squared. Now when I set each factor equal to 0 and solve, because I'm finding the zeros here, right? I say x squared is equal to 0, x minus 6 is equal to 0. You could do x minus 6 equal to 0 again, although you're not really going to need to. Here we would solve this by taking the square root of both sides, and you would just get x equals 0 again. Of course, technically you would do plus or minus, but positive 0 and negative 0 are still both 0, so that's not really going to do me any good. Here we get x equals 6, and here we would get x equals 6 again. You don't need to state the same solution more than once. In fact, technically you could do the same thing here, right? X is really x times x. So really that's two different factors. You could say x equals 0, x equals 0, x minus 6 equals 0, x minus 6 equals 0. You don't need to state what's called a repeated 0 or a repeated root. You don't have to state it more than once. However, as we'll see here in just a little bit, it does give us insights into what the graph of this thing is going to look like, what's going to happen at those zeros. All right, so same thing again here. We're trying to find all real zeros, right? So we're going to want to factor this, right? Again, if you're really good at factoring, if you're really strong at this, you may want to pause and try it on your own. If you're not that great at factoring, you can probably watch this one and then practice the next one. All right, just kind of a rule of thumb here. Again, of course, we're going to be able to do a greatest common factor, right? Both of these have a 2, and both of these have x's. In fact, they both have an x squared, right? So we can go ahead and pull that out. But another thing that always helps, I feel, is whenever your leading coefficient is negative, go ahead and factor out a negative as well. So I'm going to factor out a negative 2x squared. All right, so when I do that, I've factored out this negative, I've factored out this 2, and I have factored out 2 of the 4 x's. So all I'm left with are 2 more x's. Now I factored out a negative here, right? So I'm actually going to have to change that positive to a negative, because a negative times a negative will become this positive. All right, I've pulled out this 2, and I've pulled out the x squared. Now you do have to be careful that when you pull out everything, that you don't just leave it nothing. All right, you always have to kind of leave that 1 as a placeholder here. All right, so now we've done our greatest common factor. All right, hopefully we noticed, we went over in class last week, all right, that this is a difference of perfect squares. So this will factor further to x plus 1, x minus 1. All right, so now this thing is fully factored. Again, you could think of x squared as x times x, but you don't have to. So again, we have multiple factors. We're going to set each factor equal to 0. All right, so here we would divide both sides by -2. Well, 0 divided by -2 is still 0. Then we would take the square root of both sides. The square root of 0 is still 0. So here x is equal to 0. Here subtract 1 from both sides. X is equal to -1. Here we add 1 to both sides, so x is equal to 1. All right, so here are all of my solutions, or my zeros, if you will. Okay, use the graphing calculator to graph the following. Describe the effect of the repeated factor on the graph of the function. Right? So we kind of, in these last couple examples here, right? Here we know that 0 is repeated, because it would really be a solution twice. Right here, 6 was a solution twice. Right here, 0 was a solution twice. I mentioned earlier that that's what's called a repeated solution. Right? So that's what's going to happen whenever you have exponents above factors. Right? So what I want to do here is I'm not going to graph every single one of these, all right, but we're going to graph some of them. All right, so now we can kind of take a look at each one of these individually. So if I go to y equals, all right, first I can do x minus 1 squared times x plus 3 cubed. Oh, no, that's squared. All right, so if we go ahead and graph this thing, it will look like this. Okay, well, these are my zeros, right? If I set each one of these equal to 0 and solve, I would get x equals positive 1 and x equals negative 3. Well, those are obviously my x-intercepts. All right, and what is happening at these x-intercepts? Right, well, if we notice, right, the graph comes down and touches the x-axis. I call that a bounce, right? It kind of bounces off of the x-axis, and it does the same thing over here. All right, let's look at the next one. I'm not going to put them all on the same graph, but I will a couple of them just for so we can see the differences between them. So I have x times x minus 1 times x plus 3 to the 4th power. All right, so if we graph this thing, okay, so again, this x is going to give me 0 as an x-intercept. This factor will give me positive 1 as an x-intercept, and this factor will give me negative 3 as an x-intercept. Okay, so again, we can kind of look at what's happening at the zeros. Well, at negative 3, this thing bounces, right? And it has a repeated root. So every repeated root that we've seen so far has bounced. Right here, at x, it crosses through the x-axis. It goes all the way through. And at 1, it goes all the way through the x-axis. Okay? So kind of keep that in mind. We'll clear these out so it doesn't get too jumbled. We'll go down here and we'll say, okay, x minus 1 squared and x plus 3 cubed. Alright, so now when we graph this thing, we've got this graph. Okay, so this factor here will give me a 0 or x-intercept of 1, which is going on here, and it bounces again. Right, we have a repeated root that bounces. Here we have, if we set this factor equal to 0 and solve, x minus, or x plus 3 equals 0 would give us a 0 of negative 3, which is right here. We have a repeated root here, but now it actually goes through my x-axis again. It crosses it, okay? So this is my first repeated root that we've seen cross, right? Well, what is different between all of these repeated roots? All right, and this repeated root. We'll look at one more before we kind of discuss what's going on. And I'll go down here to number 7. So I'll say x times x minus 1 to the 4th times x plus 3 to the 7th. Alright, so if we graph this thing, alright, so again, we're going to have 0, we're going to have 1, we're going to have negative 3 as zeros or x-intercepts. Alright, so here at x, it just goes kind of straight through, it crosses through. Here at 1, it bounces again, and we have that repeated root of 4. Here at negative 3, it crosses again, and it has that repeated root of 3. Okay, so what we need to kind of notice here, and hope some of you probably remember this from Algebra 2. All right, this is really all review from Algebra 2 still. All right, if your repeated root is even, 2, 4, whatever, all right, then it's going to bounce off the x-axis. If your root is odd, 3, 7, or even just 1, all right, then it's going to cross through the x-axis. Right, it's going to go straight through it. All right. Now, there is a subtle difference between odd roots that are greater than 1. Right? So here we just have 1, and it goes straight through. Here we have 3, and you'll see it does a little squiggle. Right? So whenever you have an odd repeated root that is greater than 1, 3, 5, 7, there'll be a little squiggle here. Right? If it's exactly 1, it'll just go straight through. And any even, right, will bounce. All right, so that's what this says here. All right, so repeated roots if k is odd. Okay, and k here is the value, or actually I shouldn't call it value. We'll call k the number of times a zero is repeated. All right, so if k is odd, 1, 3, 5, 7, all right, the graph crosses the x-axis at the 0. All right, if k is even, 2, 4, 6, 8, the graph bounces off of the x-axis at the 0. All right, so you may also see this as touches. The graph touches the x-axis at the 0. I like bounces, but you can use whichever one you want. All right. So, sketch the graph of the function, use end behavior, x and y intercepts, and multiplicity of roots. Okay, multiplicity of roots, this is the repeated roots. That's what it's talking about. All right, so when you see multiplicity of roots, that's just how many times is that factor being repeated. All right. So we're going to use all of these things to assist in sketching of the graph. Okay. So let's go ahead and get some axes up here. And we'll get to 1, 2, 3, 4. Okay, so let's kind of find all of this stuff. Okay, y-intercepts are kind of going to be off on their own, so we'll go ahead and find this first. How do we find a y-intercept? We plug 0 in for x. Okay, so I plug 0 in here, 0 here, 0 here. So I'm going to get 0 times 0 minus 3 squared times 0 plus 3 cubed. Right, now, when you have a 0 out front, it doesn't matter what all this stuff equals, right? I mean, sure, 0 minus 3 is negative 3, that squared is 9. 0 plus 3, 3 cubed is 27. 9 times 27 is a very large number, okay? But who cares, right? We're multiplying all of that by 0, all right? So anything times 0 is 0, all right? Now, we can also talk about end behavior. All right, but we need to be careful, right? When we talked about end behavior earlier, we were talking about, okay, the degree of the polynomial and the sign of the leading coefficient. Well, all of the polynomials that we kind of were looking at earlier were in standard form. When a polynomial is in standard form, all you have to do is look at the highest power of x. Right? This is in factored form. This is very different. Right? In order to get this in standard form, we would have to multiply all of this out. Now, we don't have to multiply all of this out. We can actually just look at all of these exponents, which that is obviously a 1, and we can actually just add them together, and that's what is going to be our degree. So 1 plus 2 plus 3, right? The degree of this polynomial is going to be 6, which is an even number. All right. You can also take all of the leading coefficients and multiply them together. A positive times a positive times a positive is going to be positive. So my leading coefficient is going to be positive. So if we go back to that chart of ours from earlier, all right, an even degree polynomial with a positive leading coefficient, the end behavior is rise to the left and rise to the right. All right. Now to talk about x-intercepts and multiplicity of roots, all right, I like to draw a chart just to organize things. All right, so here we're going to put our x-intercept. All right, here we're going to put our multiplicity, which is basically just how many times that root repeats itself. And here we're going to say whether it is going to bounce or cross off of the x-axis at that x-intercept. Okay, so this first factor out here, if we set it equal to 0, x equals 0. It has a multiplicity of 1 because it's just the first power. Right? 1 is an odd number, so it is going to cross the x-axis at this x-intercept. If I set x minus 3 equal to 0 and solve, I will get positive 3. Right? It has a multiplicity of 2, because that exponent there is 2. 2 is an even number, right? So the graph will bounce off of the x-axis at this x-intercept. And finally here, if I set x plus 3 equal to 0 and solve, I will get x equals negative 3. It has a multiplicity of 3 because of that exponent up there. 3 is an odd number, so it will cross. All right, so now I can go ahead and kind of put all of this stuff on my graph, right? And I can get a basic sketch of the graph. So I know I'm going to rise to the left and rise to the right. I have a y-intercept of 0, which is also an x-intercept, right? I have an x-intercept at negative 3 and at positive 3. All right, so now I know at negative 3, which is the first graph, it's going to cross. And if you want to do that little squiggle, you can. You don't have to. All right. At 0, I also know it's going to cross. So I have to come up here and I have to cross. And then at 3, all right, it is going to bounce. So I'll come back down here. I bounce off of the x-axis. I meet up with my other end behavior there, and I'm done. Okay. Now, my maximums and minimums here, we don't know what my maximums and minimums are. When you get to calculus, you'll learn a way that's easy to find maximums and minimums and exactly what those are, all right? But we don't know, all right? So don't worry about them, all right? It's not going to matter how low, like if you wanted to come all the way down here and then come back up here, that's fine. up here. If you wanted to come way up here and come back down here, that's fine. Right? You're not going to be graded or judged on maximums and minimums. Okay? On a problem such as this, you're only going to be looked at, does your graph match all of this stuff, right? Did you do this correctly, and does it match your graph, right? Our graph has none of this stuff tells us anything about maximums and minimums. All right, so let's go ahead and try another one, right? Again, you very well may want to pause this right now. All right, so 1, 2, 3, 4, 1, 2, 3, 4, 5. All right, so we'll go ahead and look at all of this stuff. Y-intercept. Again, I plug 0 in for every x. It's not really going to matter what this stuff is. 0 cubed is 0. 0 times anything is 0. All right, my end behavior. All right, this is 3, 1, and 2. So if you add all of those over, that's 6 again. So that's an even degreed polynomial. All right, positive times positive times positive is a positive. So again, even and positive, I'm going to be going up, up. And then I can make my chart. All right, so x-intercepts, multiplicities, and whether we bounce or cross. All right, so first x-intercept, right, if I set this factor equal to 0 and solve, I get 0. It has a multiplicity of 3, which is an odd number, so it crosses. X plus 4, if I set that equal to 0 and solve, I will get negative 4. That is to the first power, so it's multiplicity of 1, which is also odd, so it will cross. If I set this factor equal to 0, I will get positive 3. Its multiplicity is 2 because of that exponent there. 2 is an even number, so we will bounce. So I put all of this stuff up on my graph. In behavior, y-intercept, x-intercepts. All right, at negative 4, it's going to cross. At 0, it's going to cross, and it will have that little squiggle if you care. All right, and at 3, it's going to bounce, and I'm done. Again, doesn't matter how low you come here, how high you come here. All right, it just needs to match all of this data. Okay, let's try another one. All right, now this is in standard form, so it's a little bit different than what we've seen so far. We may want to factor this, all right? So I can pull out, oops, I can pull out an x cubed, all right? And I will be left with 3x minus 4. All right, so now I can, this is in factored form, I can kind of do all of my stuff. All right, my y-intercept, if I plug 0 in for this again, 0 cubed is 0, 0 times anything is 0. All right, my end behavior. Now you can look at this one of two ways, right? You can add these, 3 and 1 gives us 4, or this is in standard form, so we know that my highest exponent is 4. Anyway, that's even. My leading coefficient is positive, so again, I'm going to be going up, up. Right, and then I can make my chart. Oh, whoops. Okay, so if I set this equal to 0 and solve, I get 0. All right, my multiplicity there is going to be 3. All right, and that is an odd number, so it will cross. If I set this equal to 0 and solve, I will have to add 4, then divide by 3. So this will be 4/3. It has a multiplicity of 1, so it will also cross. All right. So now we can go ahead and draw some axes on here. My end behavior, up, up, y-intercept 0, x-intercept 0. Guys, whenever you have a y-intercept of 0 or an x-intercept of 0, you also have to have the other one, right? Like if you have a y-intercept of 0, you have to have an x-intercept of 0. If you have an x-intercept of 0, your y-intercept has to be 0, right? You can't have a point on the origin and have it not be an x and y-intercept. All right, so I have another x-intercept at 4/3, which is 1 1/3. All right, I know that at 0 I cross, and I will have that little squiggle if you really care. I cross again up here, and I'm done. That's all we have to do. All right, find a polynomial function that has the given zeros. All right, so now we're kind of going backwards. Well, if -7 is a 0, right, that tells me that x plus 7 has to be a factor, right? If I set this equal to 0 and solve, I would get -7. If 5 is a 0, then x minus 5 has to be a factor. Again, if I set this equal to 0 and solve, I would get 5. So now all I have to do is multiply this out. I distribute. You can use the box method or whatever you want. All right, so we're going to get x squared plus 7x minus 5x minus 35. And that ends up being x squared plus 2x minus 35 when you combine our like terms here. All right, so we're done there. Continuing on. All right, here, if 0 is a factor, if 0 is a 0, then just x has to be a factor, right? If I set this equal to 0, then I'll get that. 2 will give me a factor of x minus 2. 5 will give me a factor of x minus 5. All right, now multiplication, order in which you multiply doesn't matter, so I would recommend multiplying these two first and then distributing your x through there. So if you do that, you're going to get x squared. You'll get minus 5x minus 2x, which is minus 7x, and then plus 10. And then when you distribute that x through, you'll get x cubed minus 7x squared plus 10x. And we're done there, right? I do also want to show you how that can work with imaginary zeros, because it gets a little tricky there, all right? When you solve any equation, you saw this a lot in Algebra 2 with quadratics, right? You can definitely get imaginary or complex solutions, right, of the form a plus bi. So what if your zeros, all right, were 0, -2, 1, well, I won't do that, that'll get a little messy, get a little tricky. All right, what if I say, 3 plus 2i, right? This is a complex solution, all right? So I said, okay, find a polynomial that has all of these as solutions, okay? I mentioned earlier, and again, you should remember this from Algebra 2, that complex solutions always come in pairs. They're called complex conjugates. So if 3 plus 2i is a solution, all right, we need to know that 3 minus 2i is a solution as well, okay? It won't be given to you, you'll just have to know that the complex conjugate must also be a solution, all right? So if I'm trying to find this polynomial, all right, 0 is going to give me x as a factor, -2 is going to give me x plus 2 as a factor, all right? 3 plus 2i, basically what you're doing is x minus whatever your 0 is. So here you'll say x minus, and then in parentheses, 3 plus 2i. And then we'll also have to use this one, x minus, and then in parentheses, 3 minus 2i. All right, so I'll kind of keep these to the side here. All right, I'll go ahead and distribute this negative through. So here I'll get x minus 3 minus 2i, and here I'll get x minus 3 plus 2i. Okay, now when you go ahead and multiply these things together, all right, make sure that you multiply the imaginary pieces with the complex conjugates together first, all right? And you can multiply these things together as well. That's perfectly fine, but I would kind of wait till the end to these things. So I'm going to keep this, x times x plus 2. All right, now when I go ahead and distribute all of this stuff out, again, you can use your box method if you want. X times x is x squared minus 3x plus 2xi minus 3x plus 9 minus 6i negative minus 2xi plus 6i and minus 4i squared. Okay, so this looks pretty messy here, and it is. All right, but some things work out nicely. This minus 6i plus 6i, all right, plus 2xi minus 2xi, all right, and do remember that I squared, well, first of all, I guess, remember that I is equal to the square root of negative 1. So I squared is equal to negative 1, right? So if I squared equals negative 1, negative 4 times negative 1, this is really just positive 4, all right? So cleaning this up a little bit, I have x plus 2, and now I'm going to have x squared minus 3x is minus 6x. Here I have plus 9 and plus 4, all right? That's going to be plus 13. So now I can just go ahead and multiply all of this stuff out. Again, I would leave the x until the end. It's really easy to just distribute through. So now I'm going to distribute again, or you can use your box method. This will be x cubed minus 6x squared plus 13x plus 2x squared minus 12x plus 26. All right, again, cleaning this up. All right, we're going to have x cubed negative 6x squared plus 2x squared is minus 4x squared. All right, 13x minus 12x is just plus 1x. And then we have our plus 26. So distributing this x through, we get x to the 4th minus 4x cubed plus x squared plus 26x. All right, so there is our 4th degree polynomial, which that makes sense, right? Because we had 1, 2, 3, and then of course these always come in pairs, so 4. So we have 4 solutions, so we should have a 4th degree polynomial. All right, find a polynomial with the polynomial function with the given zeros, multiplicities, and degrees. All right, so here we have a 0 of 3, which means we should have a factor of x minus 3 with a multiplicity of 1, so that's just to the 1st power. All right, here we have a 0 of 2, which would be a factor of x minus 2 with a multiplicity of 3, so that's to the 3rd power. All right, and a degree of 4, well, 1 plus 3 is 4, so that is a 4th degree polynomial. All right, we're done. I wouldn't make you multiply all of this out and put it in standard form. All right, so on the test it will say do not expand, All right. So if it says do not expand, you just leave it here. Okay. If it says to expand, all right, like this, all right, this is what we did. This was my expansion. All right, same thing here. Find a polynomial function with the given zeros, multiplicities, and degree. All right, so it says a 0 of 1 with a multiplicity of 2, a 0 of 4 with a multiplicity of 2, a degree of 4, and it wants you to fall to the left and rise to the right. Okay, now, usually when I have all of my students in person, I kind of give this as a trick question, and I hope that usually several of my students in each class figure it out. So if you want to pause the video and try to figure out what the problem is with this, that would be excellent. Right? If not, it's okay. I'll go ahead and explain it now. Right? You can't do this, right? Because a degree of 4 is an even number, so that's either going to go up and up or down and down, right? Falls to the left and rises to the right. This can only happen with an odd degree. Right? So you can't really do this, okay? But just for practice and explanation purposes, right? Let's go ahead and change this to false. All right, so I say, all right, well, I have a 0 of 1, so that's a factor of x minus 1, multiplicity of 2 to the second power, 0 of 4, so that's x minus 4, multiplicity of 2 to the second power, degree of 4, 2 plus 2 is 4, I'm good, falls to the left and falls to the right. Okay, well that means I have to have a negative leading coefficient, but right now I have a positive times a positive, right? You don't need, like if you put a negative inside of here, that actually messes up your 0, so you'd have to change this, it gets all messy. The easiest way to do it is if you need to have a different leading coefficient, is just throw a negative way out front here. Okay, so there we go, I'm done. Okay, the intermediate value theorem. This is something that typically confuses students. Right? It sounds very complicated. It's not really very complicated, but it definitely sounds that way. The definition of it is, and even the visualization of it is, to a point. But the application of it is actually very easy. So if you don't fully feel that you understand the definition or what it's really saying, all right, that's okay. All right. The application of it is going to be much easier than what it, what the actual theorem looks like. But we'll go ahead and go over the theorem anyway. All right, so the intermediate value theorem concerns the existence of real zeros of polynomial functions. The theorem states that if a point a comma f of a and another point b comma f of b are 2 points on the graph of a polynomial function such that f of a does not equal f of b, then for any number d between f of a and f of b, there must be a number c between a and b such that f of c is equal to d. All right, so again, that is kind of really complicated. All right, so I'll kind of go ahead and, although there's a graphic on the next slide, it's kind of all there at once, so I think it's a little bit easier to kind of build you the graphic, if you will. So if I have some function, and some polynomial, so it's nice and smooth and continuous, all right, and we have like that. So it says, okay, for any points a f of a and b f of b, all right, so I'll say, okay, so I have some x coordinate here a and some x coordinate here b, right? Of course, the point that it corresponds to on the graph would be right here, right? So over here, this would be the y value f of a, and here corresponds to this point here, get a little bit messy, but whatever. This is supposed to be completely horizontal, so don't hate on me if it's not. All right, this is f of b, some other y coordinate, f of b. All right, so that's this would be my point a comma f of a, and this would be my point b comma f of b. All right, so it says if we have these points, all right, and f of a does not equal f of b, which they clearly didn't, then for any number d between f of a and f of b, all right, so just pick any point in between here, and we'll call it d. It's not really going to be a point, it's going to be a y value. Then there has to exist some c, which is an x coordinate. So this would be my c between a and b. All right, that gives me this d value. Okay, that's what it said. Right. There must be a number c between a and b such that f of c equals d. So here's my c such that f of c equals d, right? Because this would be the point c comma f of this would be the point cd, which f of c, of course, equals d. All right, so again, this looks kind of messy, but again, kind of remember what it said, that it helps us find the existence of zeros. Okay, well, zeros are x-intercepts, right? So if this is my d, all that it says is that there has to be a zero in between here, right? How we're actually going to apply this, right, is that if I'm on a graph and I have some point where I have a y, a positive y value, right? This is a positive y value. And if I have some other point that has a negative y value, and if my graph is continuous, there's no possible way that I can get from a positive y value to a negative y value without crossing the x-axis. That's all that this thing says, right? So if I have a positive y value and a negative y value, that's somewhere in between there, I have to cross the x-axis. That's really all that it's saying. Right? Here is the graphic, which I don't think really does a whole lot. Okay, so on the test, the application is even going to be easier than this, right? But we'll go ahead and do what they ask us to do here. All right, so find 3 intervals of length 1. So, intervals of length 1 mean from like 0 to 1, 1 to 2, 2 to 3, right? 7 to 8, okay? In which the polynomial function is guaranteed to have a 0. Okay, so really all I have to do is start finding function values, right? Easiest function value to find is f of 0. So if I plug 0 in for x into all of these, bam, then this will be 0, this will be 0, this will be 0, this is 5. Okay, well, what's another really easy number to plug in? 1. All right, so if I plug in 1, 1 cubed is 1, 1 squared is 1, whatever. So this is 12 minus 32, which is negative 20, right? Plus 3, which is negative 17, plus 5, which is negative 12. Okay, so I've already found 1, right? I can't go from a positive y value to a negative y value without crossing the x-axis, without there being a 0. All right, so one of them is from 0 to 1. All right, what's another easy number to plug in? How about negative 1? All right, well, negative 1 cubed is going to be negative 1. Negative 1 squared is going to be positive 1. And then, of course, this is just negative 1. So I get negative 12, all right, minus 32, which is negative 44, minus 3, which is negative 47, plus 5, which is negative 42. So again, from negative 1 to 0, I went from a negative to a positive, all right, which means that I had to have crossed 0. So from negative 1 to 0. All right, so now we have 1 left. All right, let's try 2. Right, now you may need a calculator for this, all right, but this is going to be 8, so 96. This is going to be 4, so 128. 96 minus 128. All right, and then we're going to be adding 6 in there, and then plus 5. All right, so that ends up being negative 21. So we didn't change, right? We were at a negative, we stayed a negative. Okay, well, let's try 3. All right, 3 is going to be nasty. All right, so just plug it into your calculator. That's no big deal. All right. All right, and if you do that, you're going to get, you're going to get 50. Okay, well, we went from a negative to a positive. All right, so between 2 and 3, there has to be a 0 as well. So there's our 3 intervals of length 1, all right, and we're done. All right, that's going to be all for today. You will have an assignment on Delta Math that will cover most of this as much as I can, and we'll be done there. Also, guys, this is going to be a very, very short unit, all right? So you're going to have probably another test over this stuff on Friday. All right, we're just going to do what we just covered today. We're going to do one more lesson tomorrow. Then we'll review Thursday, test Friday. Have a good day.